or is it pretty much a constant, or no matter what system you're in?
So stars emit some microwave radiation. So if you want to see the CMB precisely, you have to subtract what comes from the star. But it's very easy to do because the star passes through the sky, in our case the sun, from the Earth, passes in the sky every 24 hours, more or less on the same path. So what comes from the star will vary across the day, and what comes from the CMB will never vary. So even at night, when you're shielded from the star by all of the mass of a planet, even then you'll still see the CMB. It will be the same, even when you're perfectly shielded from the star. So in theory, it shouldn't affect it. And if it does, it's easy to account for. You just wait.
You can basically filter out any influence that stars or planets can have. That's an easy thing to do, right?
Yeah, and it's not even the only thing we have to subtract for. So even the galaxy contributes a bit. Mostly scattering of starlight by the dust that's floating around can transform starlight into many wavelengths, including microwaves. So we have to subtract that contribution too, and that's a bit harder to do. It means that basically where the Milky Way is, we can't really see the CMB. It's hidden behind all the dust of the Milky Way. So you have to look perpendicular to the Milky Way, where it's really clean. So that's where you get the best signal.
So hypothetically, trying to measure the CMB from another star system, maybe where there is a more direct line to the outside of the Milky Way, would be beneficial.
It would be a good test to actually do the subtraction correctly. Although we're pretty confident we do, because we've subtracted all the things that made it vary in whatever way. So it doesn't vary with pointing, it doesn't vary with time. So we think we've disentangled all the different components pretty well, but it would still be a good test to measure it from another place.
It's still best to measure it, try to minimize the interference from other phenomena.
Yeah,
right?
For sure.
So if you try to measure it from, near a black hole, that would be stupid.
And there's even worse stuff. From a black hole, that wouldn't be great. All the gravitation will be distorting the light. Probably not the best. If we could measure it from outside the galaxy, it would be even better, because actually our sun is moving with respect to the galaxy. Right? The sun is going around the center of the galaxy reasonably fast. And so because the galaxy is what's really at the center of mass of our local cosmic web, the galaxy doesn't move compared to the CMB, but we kind of do a bit. So the CMB is moving slightly compared to us. It's what we call the CMB dipole. So
it's moving in the sense that it's receding, right?
We're kind of heading towards one point, because our galaxy is stationary, but the sun goes around the center of the galaxy. So we're kind of heading very slightly towards one angle.
So it's kind of a bit of a Doppler effect then?
Yeah, it's a Doppler effect. So you see one half of the sky slightly getting closer and one half slightly getting further away. On the axes, we're going around the center of the galaxy. So if we could not have that would be, I guess, easier. But then again, that's an easy effect to subtract, because we know how fast we're moving, so we know exactly how much that is. So it would be nice, but not game-changing.
Well, we'll see. Maybe one day we'll be able to send telescopes that have the Milky Way, but I don't think it's going to happen anytime soon. We have another rather complicated question from Mike, Rusted Bulk Mike. I'm going to skip that one. I'm sorry, Mike, if you're listening to this. We're going to get to your question, but it is a bit specific, so I'm going to skip to some more. I wouldn't say simple, because they're not really simple, but more straightforward questions. That Michael, who is here listening to us, and he is responsible for actually setting up the broadcast today, but sadly, he is a bit tired. He is not able to speak. But he did submit a question earlier, and he's asking what's the difference between the CMB and the particle horizon, which I'm not sure what that is myself. What is that? Well,
it would be probably best to start with a good definition of what the CMB actually is. What are we actually seeing? Because we need to understand that to answer this question.
I thought you... Okay,
So,
well, that's what I asked earlier.
Yeah, but where does it come from? You know, the CMB is this limit that we see.
Want to go from that. Okay,
but where does it come from?
Let's go from the actual start now.
Yes, all right. So we know all the galaxies around our Milky Way are moving away from us, apart from Andromeda, which is really close, so it's actually attracting. But all the major galaxy groups are all moving away from each other. So our local cluster is the Virgo cluster, and is moving away from all the other clusters at a pretty much constant speed, depending on distance. So all these clusters are moving away from each other, right? So you wind back the clock. It means that they were closer, like slightly closer a few years ago. And they were even closer a billion years ago. And if you keep going back and back, you reach 13.7 billion years ago. They were all more or less on top of each other. And that's the first evidence for the Big Bang, that that all these things are moving away from each other, so you just wind back. Now, what happens if a lot of things came from one point is that, the pressure increases. You press together all these galaxies and stars and the gas they're made from, and you get a very thick soup. And when the density of the universe was high enough to stop light, light could not travel from this primordial, very dense gas thing. And that's pretty much the limit of what we can see. Because if light cannot travel through fog, we cannot see what was before. It's like a wall to us. And that's where the CMB comes in. So if we go from the start, imagine the universe is really, really full of glowing fog. That's what it was. It was superheated plasma. Not even that strange. We can make this stuff in the labs, right? So it's the kind of material we've created already in Earth labs. So it's very dense and it's glowing. So at some point in this enormous universe, about 100,000 years after the Big Bang, or the initial point, all of this fog is going to suddenly become transparent all at the same time. So it's all going to vanish from everywhere all at once, because it becomes just cold enough that it stops glowing and light can come through. And that's where we get the CMB from. So I have an analogy for this, which some of you may have heard before. So if you imagine, if you can, that you're standing in an infinite field somewhere outside, and it's covered in fog. You can't see anything. You can only see your own feet. You have no idea what's around you. There may be trees scattered all around you. You can't see any of them. So imagine this field is infinite, completely covered in fog. And then at some time, all of the fog is going to vanish from everywhere at the same time. There's going to be no more fog left. But you won't immediately see everything. If there's a tree quite close to you, you might see that one first. It doesn't take long for the light from that tree to now come to you. When it used to be covered in fog, the light was stuck in the fog. It couldn't go towards you. So as soon as there's no fog, it starts on its journey towards you. And say 1 light second later, it's made it to you, and you can see that tree. That's great. But a tree that's at 5 light seconds away from you, you can't see that one yet. It's still, the information from that, the light that's free to come towards you, still hasn't reached you yet. So at first you can see the trees close to you, and you can't see the ones far away, even though they're already there, and there's no more fog anywhere. So what do you actually see? If you're standing there and you see some trees that are close and not trees that are far away, it would actually look like a wall of fog. You would see yourself surrounded by a big circle of fog, which doesn't exist anymore, but you don't know that the fog at that location doesn't exist anymore. So you would see this wall all around you that's moving away from you really fast. And that's the CMB.
So basically, the CMB is already no longer there.
Yeah, it's already no longer there. That type of plasma that launched this light doesn't exist anymore. But we still don't know what's behind it because we haven't had time to see it yet.
Right. So basically, it's like there's a blanket that is being gradually pulled away from fun things, but we need to wait for it to be pulled away completely before we know what's beyond it.
Yeah, and it's actually still moving away from us. The CMB is getting away from us every day.
Because it's the light that is reaching us gradually, and we see, like in your analogy with the fog, we see more and more every day because light reaches us more and more every day.
From that location, yeah.
Exactly.
Which in reality already has lots of stuff in it, we just don't know it yet. So it's not the edge, it's just the edge of what we have had time to see.
So it could be, okay.
There could be a ton of stuff beyond it.
Exactly. It could be even like more than what we currently think there is.
It could be literally infinite and we wouldn't know. But that's as far as we have had time to see.
Yeah, and there is not much we can do about that. I mean, not even technology can save you from the speed of light. I mean, you need to follow it, right?
Yeah, pretty much.
So even if we somehow devise a method to see the CMB perfectly without any interference, you can't make light go faster, right?
Yeah, and that's exactly the question that you asked me earlier. What's the difference between the CMB and the particle horizon? Well, the CMB is when this light was able to escape. The particle horizon is when a specific particle was able to escape, which might be earlier or later. It could be earlier if things like neutrinos were able to escape the fog first. They require higher temperatures of plasma to keep trapped. So they're harder to trap, basically, which means when the universe was cooling, they might have escaped the fog first, slightly earlier. And then then that horizon, the neutrino horizon, might be a bit further away.
But we can't really use it for anything.
Well, we can see slightly further away.
So we can map the universe just by using neutrinos?
In theory, you could see a neutrino background of all your neutrinos that escaped then, and by now they all have the same energy.
In theory, in the sense that it hasn't been done.
It hasn't been done yet, because detecting neutrinos is really freaking hard.
Right.
You know how freaking hard it is? They have this thing called Ice Cube, which is the coolest thing.
Because
on all of Earth. Ice Cube is the coolest thing that man has ever built, in my opinion. They have this, it's in Antarctica, and they have a cube in the ice that's 1 kilometer by kilometer by 1 kilometer on the side. That's just cut into the ice. 1 kilometer on the side. That's even too big for me to imagine.
You're a cosmologist. I think you can imagine quite large sizes.
I know, but that's like in the awkward middle, where it's a distance that you can kind of understand what a kilometer is, and you imagine a kilometer up and a kilometer across. You're like, damn. And that's a neutrino detector, right? That's what they monitor. And every time a neutrino goes through this ice cube, it has a small chance of like interacting with the water in the ice. And if it does, it makes a tiny light flash. And that's how they find neutrinos.
Why water? Isn't there any other material that is more reactive to neutrinos?
No, and water's pretty good because it's very dense, it's very heavy for the volume. And if you use something like metal, then you couldn't see the light flash. so it's actually heavy water. So it uses heavy hydrogen, deuterium.
And I imagine water's slightly less expensive.
Yeah, probably. And in Antarctica, I guess you can find a lot of ice. Cutting it out, assume. But again, we don't detect as many neutrinos as necessary to map.
No, we haven't really seen a neutrino background. But then again, it's also hard to know where they come from. Like, we see neutrinos coming from deep space once in a while. We don't really know where they came from.
Yeah, I agree, Mike. Mike is saying that he loves this foggy field analogy. And I have to agree, because even people that understand and know what the CMB is, at least in my case, I always thought of the CMB as an actual wall of radiation that basically opaque, so you can't see through it. But it actually never occurred to me that it doesn't really exist anymore. And the simple reason we see a wall is because the light hasn't reached us yet from the wall. So this fog analogy helps us realize that it's not there yet. It's just light of stars. We see the past as we look up, and the CMB is just that. It's just the past, but it doesn't exist. This is actually a good analogy. Makes you realize that what you see is not necessarily what is.
And not necessarily the edge.
It's the same idea as like what the other galaxies out there. We're just seeing of whatever.
Sorry, I didn't catch you.
So you're breaking up. Hello, Pookie.
Hi. Do I need to speak up?
Yeah, you kind of do.
I'm sorry. Basically, what we're seeing, like past light, is we don't know how much of the galaxies that are around us. since they're all moving away, right? So we're not even sure how they changed. But then we see them.
Yeah, that's true. Some of them are really far away, so we don't really know what they've done since. Except, in a way, we do, right? Because the more far away they are, the more we see them like they were in the past. So it's a bit like you're digging up layers. If you're an archaeologist, the deeper you dig, you see things as they were back then. So we can see how galaxies have changed on average since when they were born all the way to today. They've had a very complicated life, very dramatic.
Dramatic, lots of drama all around.
Lots of drama in galaxy evolution.
Great, they can make a show out of it.
Well, they have to speed it up a bit, probably.
Yeah.
Yeah, maybe.
So if that's
anyway.
if that's actually true, some say that in Andromeda coming, but shouldn't it be moving away? If that's the case, about everything moving away. So
can you say again?
Sorry.
Can you say again, Pookie? Sorry.
I'm so sorry. Basically, I know that we can see all this life and stuff, lights, but wouldn't it change if the galaxy is actually coming towards us? For example, I believe it's Andromeda is coming towards us, or is that untrue?
Andromeda is coming towards us, but it's very close to us.
Are you talking about redshift or what?
Yeah, I think she's talking about blue shift and red shift.
Yeah, galaxies on average move away from each other, all roughly at the same speed from their neighbors. On average, if two galaxies are very close together, they can still collide. Gravity still attracts them. It's just on large scales they're moving away. And definitely on the scale of clusters of galaxies, these are really good measuring points because they're really heavy. And compared to each other, they follow this very closely. As a rule, if something is twice further away from us, it's moving away twice faster.
Okay, that's quite interesting. It's a coincidence, I guess.
No, it's
not really a coincidence.
That's how linear expansion works, and it's roughly linear.
Yeah, I should stop talking. And yeah, this was supposed to be a quick question, but actually it wasn't.
I think it's a good way to lay the ground for the other questions, which you said a lot harder. I'm bracing myself.
Okay. Oh, I have Ashnak here, who is another physicist. He's saying that you may have been mixing up the ice cube, Super Kamiokande, and Sudbury, and there were detectors using metals.
Yeah, I got confused with the heavy water thing. Ice cube is normal water because you can't really get a square kilometer of heavy water.
So the ice cube is still used for neutrino detection, right?
Yeah. They all the things that they named ice cube, Kamiokande, and Sudbury. They're all neutrino detectors.
Okay. Well, no, thank you, Ashnak. It's actually good to have experts here. So it's another wall of text. Okay, come on, selfish spy. I mean, you're doing it on purpose. Okay, you can jump on. You can jump on voice. You know, people want to hear your Scottish accent.
I believe he can't. He doesn't have access to this channel.
Oh, right, because he's a pleb. Anyway, we're going to jump to the next question, which again is it is shorter. So this is actually from Selfish Boy. He likes questions, so let's go with that. So the CMB tells us the past, right? It tells us we look back into the past. We have now discussed about. But is there anything that we can infer from it that gives us a glimpse of what the future would look like? Does it have any impact on what theories are evolving from it that tell us how things will be and not how they were?
Yes and no. That's a complicated one. Right. So because
they always look simple, but
come on, that's a hard one. Like summarizing. Well, the thing is, because the CMB is this wall of light that we see, and we can't, like, observationally ever know or observe for sure what was before. In the end, any theory of cosmology that you have, which predicts the CMB correctly, is possible. And unfortunately, we already have a lot of those. So there are some simple ones and there are some more exotic ones. But there is more than one theory that can get us to that point of very dense plasma gas. And after that, with the CMB, the details of the CMB, and later the first galaxies, all of that stuff kind of comes from that. If you get the universe to have dense hot plasma, the rest kind of follows. So that's the short answer. The long answer is it rules out a lot of things, but it still permits more than one thing. So theories like the big crunch or the big bounce that used to be popular a while ago is still not ruled out. We don't know if the Big Bang at the start was unique or if it just expands and accelerates for a while and then eventually it will crunch back again. That is still permitted by the CMB and what we see. And then other things like a small amount of primordial black holes, that's still allowed. String theory is still allowed. So it's really a case of, we need to find other ways to distinguish these models, because at that point of the CMB, there's already more than one. In this case, scientists like to go for the simplest one. So Occam's razor, you pick a theory with the least number of variables and assumptions.
Doesn't mean it is the correct one, though.
Yeah, but how many can you investigate if you have 10 or 20? I mean, one thing that we know for sure is that before the CMB, the universe used to be even denser. So there was a point where it was even denser. A singularity in itself is not entirely sure. If it bounces from a very small radius, that's still possible. But it wasn't the start of the CMB. There was a bit before when it was even denser. Exactly how dense or what the limit was, we don't know yet.
But the thing is, we can't really afford to wait for billions of years. Well, maybe humanity will, but current scientists can't really just sit around and wait for the CMB to lift.
Yeah, no, we're designing lots of other tests.
So there are ways that we can more or less find out what's actually happened without having to look through the CMB.
Well, the CMB is the best piece of evidence we have because it's so high res, like beautifully resolved. Such a nice image, you can zoom in forever.
Okay.
The Planck satellite was wonderful. Everyone was really happy.
But still, it is also an obstacle, in a sense.
Well, it's state of the art, We always want to do better, and there are things that we can do. For example, we don't know the polarization of CMB photons yet. That's an information we don't have very accurately yet. And that could help us to test like these string theory models, these black hole models. They would have an impact on that. And currently a lot of people are making predictions on how much polarization you should see, so that one day when we see it, we'll be able to say which ones predicted it correctly.
So even with this barrier, there's still a lot of stuff that we can do.
Yeah, and the particle background that you mentioned earlier. So if we could see the neutrino background, that's again one extra stuff that we can predict things for and then see who was right, if anyone.
Right. So you mentioned briefly these primordial black holes. We have another question from Shaggy-Dog, actually, that goes into that topic. And he's saying that sometimes it is mentioned those primordial black holes could explain some of the missing mass in the universe. I assume that he's referring to dark matter.
Yeah.
He says that these, as you actually mentioned them, they are linked somehow to the CMB. Is there an actual connection about this? And do you think that those primordial black holes could be a possible explanation to this dark matter thing?
In terms of the CMB, they do leave a very specific imprint, and actually that's one of the things that will affect this thing I mentioned, polarization, what experiments like BICEP2 are currently working on measuring. So primordial black holes will change what direction the light prefers to go into. So if in this fog you already had tiny black holes, they would make light kind of converge to them. They would give a preferred sort of convergence to the photons, which we call polarization in physics. So if we can see that tiny effect, if we can measure it, it will prove there were primordial black holes already then, or at least very small compact objects that could bend the light and concentrate it in this way.
Okay.
Now, primordial black holes making up dark matter scientifically has been almost disproven.
Well, maybe not all of it, but
there's really not much room left. So we've looked for them in many different ways. We still haven't found them. There is a lot of evidence that if there are there, they're really rare. The constraints on how many you could have and still not be detected, very tight constraints.
Would they be supermassive black holes or
not necessarily? Intermediate mass is the only ones that are not completely ruled out.
Okay.
As far as the latest research has gone, is because if they're small, you need a lot of them to make up for the missing mass, even for half the missing mass, even for 10%. You need so many small black holes
and you also
that we'd see a ton of them. No, not if they're like sun mass. If they're the mass of the sun, you would still need a ton of them. Like you would still need, 4 or 5 times as many black holes as stars.
Ooh.
Oh.
So we would have seen them.
Yeah, it's hard to miss.
So those are a bit of a problem.
Can you imagine at least 5 times as many black holes as stars?
That would be interesting. I would crash repeatedly. And then at the other end of the scale, if they were supermassive, then they would lens the light behind them. And lensing by supermassive black holes is something we use a lot in cosmology to probe very far away distances and such.
So you would notice that.
So those have actually been looked for explicitly. So people have monitored large parts of the sky just in case a supermassive black hole drifts by.
Okay, by
and it's never happened.
Devour our solar system.
Yeah, but by now we should have seen them. That's the point. If you observe for long enough and you work out how many you should see and you don't see them, they're probably not there. So right. Intermediate mass are the only ones that we might have missed, but it's really closing in. It's really like almost completely debunked.
Okay. Well, I'm going to jump in a second with one little question of mine. It's going to be brief, but since we're talking about these black holes, is it true that at any given point in time there could be a black hole heading towards us and we wouldn't know until we are dead?
Yeah, it depends how fast it's going.
So it is possible.
Well, if it's moving at the speed of light, yes, you would not see it coming.
I don't think. Can black holes move at the speed of light?
Why not? I mean, nearly 99% the speed of light.
So
you would be hard pressed.
We could die in the next minute.
That would be fun, wouldn't it?
Yeah,
no,
fun.
It's not.
Fun
It's not ruled out scientifically to die in the next minute.
If it was coming towards, say, Earth from a gap in the galaxy where there's nothing else, so we can't see it eat a star, we can't see it distort any light. If it was coming from exactly that angle, very fast, yeah, we'd have no idea. I mean, it's black. What do you expect?
Well, it's even if it is small, I mean, would you still be able to see it?
If there's something behind it,
and even if you see it, what can you do to stop it? Even if it's slow, and you say, "Oh, there's a black hole coming in a year's time, it will be here." What do you do?
That's a good question. I don't think you can do anything. You evacuate.
Well, how much time do we have?
The Earth. It depends how fast it's going.
Well, that's the point. Yeah. But there is this possibility. I just want to cheer everyone up that technically we could all die tonight.
I mean,
it might not be terribly comfortable.
It will not be. It would be terrible.
Well, you don't realize it.
You would, because of relativity. The deeper the gravity well, the slower apparent time goes. So
but you would be sleeping. It's tonight, right?
It would still be very painful, you know.
You'd be woken up by the whole spaghettification thing.
Yep, you'd be torn to shreds very slowly. Well, not very slowly, but from many points at once, it would be torn to pieces.
It would feel like it was very slowly.
This is clearly...
Yeah, it would actually feel like it was. No, it would look like it was very... For someone on the outside, it would feel normal speed to you.
My opinion that this would be quite fun is clearly quite uncommon, but I would quite enjoy that because I'm not sure on the validity of this. Maybe you can confirm or deny, but I've been told that if you were to look back on the universe after you pass the event horizon, if you weren't immediately torn to shreds or burned or just died, you would be able to see all of time. Is that true?
It depends what kind of black hole it is, actually. There is this theory that if you have a spinning black hole, there is a region inside of it.
The ergosphere.
Yeah, the ergosphere, where time goes in a loop. And that's predicted by GR, but not exactly tested.
But it should be like that. I mean, mathematically...
Mathematically, it is like that.
I mean, how would you test it?
So if you get stuck into a looping black hole, you are basically omniscient.
Groundhog's Day.
You would see everything forever and back.
I think you'd be dead.
Yes, apart from that.
I'm not sure how you'd see. Your eyes wouldn't exist.
Well, I use see metaphorically. Yeah.
You'd be able to look at your side and see the back of your head.
Yeah. I thought the depiction in what was that movie? Interstellar. The depiction in that wasn't actually bad. It was decent sci-fi.
Okay.
The hypercube and all the things.
It's the first time I've heard that.
Future being linked. I mean, it's good sci-fi. It's something that we wouldn't really know, and try to make it vaguely plausible. No complaints. We don't know, so they can have artistic license.
Fair enough.
Okay, but it is technically possible. What?
Theoretically possible.
Theoretically possible. Okay. Well, that's good. Maybe
we
will use them to invent time machines or something like that. Eventually, when we can use their power. But anyway, this was just a side question. But yeah, going back to the question that Rusted Bulk Mike asked yesterday, it is back to the CMB. I'm going to read this a bit because, well, he's saying that currently our best tech can map the CMB from the recombination/photon decoupling events. I'm sure you're going to explain what that means. After the universe became transparent for the first time, he's mentioning that scientifically accurate sources, Wikipedia, status that this is roughly 377,000, I guess, light years.
Yes.
After the Big Bang. He's asking if it is physically possible to build more sensitive telescopes or other arrays that can peer further back. I mean, this is what we asked earlier, but I just mentioned this because he is mentioning this recombination photon decoupling events. I don't know if you want to expand on that, because
it's what I tried to explain earlier with the fog. So photon decoupling is when a photon decouples from the primordial plasma. So it used to be coupled to it. It was bouncing around because it's coupled, it's stuck. Then it decouples. That means it can travel through. That's just a technical term we use.
Okay.
It's a lot like fire. Fire is a superheated ionized plasma. You can't see through it because all the photons are busy bouncing off electrons in the fire. So it's like the universe is full of fire. That's a bit dramatic.
Isn't that what's happening with the inside the core of the sun where the light is actually produced?
Yeah, that too. That's also superheated ionized plasma.
Mm-hmm.
So not too different as a concept, except probably more dense.
And a lot hotter.
And a lot hotter. Well, at the point where the CMB gets launched, just cool enough that light can escape, so it becomes transparent, colder than the sun by then. I think. I should know this. I don't know the exact temperature at recombination. Shit. Know this.
Well, not prepared, Dr. Bosman.
I am not.
Anyway, we have another question. He is labeling this as a simple-sounding CMB question. We all know that there are no simple questions apparently tonight. But, we have already established that the CMB is there. But how long will it take to disappear from our view? When will it be so cool that it will no longer be detectable? Or will it always be detectable, no matter what? Somehow, even faintly, but it will always be detectable.
It will always be detectable. That is the answer. There will always be a background of some sort.
Will it be too faint for... we can't know technology, how much it will be improved, but is there a minimum amount that is physically impossible to detect that will eventually reach, the CMB will eventually reach? A minimum level of energy?
Hard to say. Depends how the good technology is. So photons will always come to us from the CMB. Now it's going to keep cooling down compared to us. And because of the joys of accelerated expansion, it's actually going to cool down slower and slower with respect to us because of weird time distortion effects. But it's still going to always cool and cool down slower and slower, but it will always be there.
It's going to be going farther from us faster, but cooling slower.
That's how we will see it. Because accelerated expansion is a fun game to play.
Why can't anything be simple?
Accelerated expansion, no one wanted it. Don't worry. When they covered it, the Nobel Prize, I'm sure they still didn't want it.
They regret it. Shit,
before the universe was simple.
We didn't want this. Okay, well.
So yeah, it will pass from microwaves to radio eventually, probably in 10 factor of 10 wavelength. 100 billion years?
Yeah,
okay.
We got a bit of time.
It will be radio, back of the envelope estimation.
Okay.
I'm bad at live maths, don't take my word for it. And then it will pass to ultra low frequency photons, and there's lower and lower frequency, but there will always be photons coming to us.
Well, we can't even say, oh, technology will be good by then, because probably humanity will not be there. So whatever will be there, if anything, will not be us or any sort of thing that resembles us. So
even then, I was thinking, is there a minimum energy for a photon according to quantum mechanics? And the answer is no. Photons can have as low as an energy as they want to. There is no maximum wavelength. Eventually, the wavelength will be the size of the universe, mind you. But there's no theoretical limit. It can keep getting lower and lower energy forever.
Right. Well, we have just to pick a follow-up question. Just if you can answer this quickly, he has a question about how the CMB get farther away from us. I mentioned that because of basically expansion, but just want to give a quick answer to that.
Yeah, I think I'm looking at the chat. Someone already answered. That's good. Yeah, so it's the fog. In. Fog is gone. The matter that you see in the CMB doesn't exist anymore. It hasn't existed for billions of years. But you still see this edge. And the amount of information that reaches us comes from slightly further away every day.
Oh, sorry, I didn't. I'm gonna mute myself. I'm gonna type. I didn't realize my. Yeah, I'm gonna mute myself.
Okay, but people like your Scottish accent. It's fun.
Well, if they like it so much, I think I might keep it.
You have a choice.
It's all right. Well, we have coming in from early today and yesterday. I'm trying to more or less keep the more vague and philosophical at the end. But we have a question from, I guess, IOI Parsible. I'm not sure if I'm reading this correctly, or 101, or face with two arms.
I think it's a reference. I think it's a reference to the Ready Player One movie.
Oh, I haven't watched that actually, so I don't know.
Is it any good?
Yeah, I thought it was good.
If that's the case, I apologize. But Parsible, concerning the physics of, what would you see if you were traveling faster or same speed than light and looked backwards. Technically, in Elite Dangerous, we do travel faster than light for some reason. And my understanding is that the ship HUD kind of simulates what you would see if you were not going faster than light. That is the bullshitty explanation of how we can actually see things in Elite while going 2,000 times faster than light.
It depends exactly how the frame shift drive works. Because saying it bends space-time to accelerate us isn't really precise enough. It depends exactly how it does that, what you would say. If, say, you were teleporting short distances, like the name implies, you only clip onto space-time with a frame and you skip frames. It's a frame shift drive, right? So you're shifting your frame, basically teleporting short distances. Then you would be fine because your inertial speed wouldn't accelerate the photons in front of you. So then you might see something pretty nice. Then maybe the HUD simulation isn't too bad if that's how it works.
So you're not actually moving, you're saying?
If it's clipping across the surface by small teleportation jumps. So basically you're folding space-time onto itself and just only touching it in some points or some frames.
So you would have a shitty frame rate.
Yeah, if it's lag, if the frame shift drive works as lag.
Okay.
So when you turn up you overclock your GPU to use the frame speeds to cheat, like in Fallout 76. If your frame rate is too high, you can actually force the game physics to go faster.
I've never done that, but I take your word for it.
It's a common video game hack that people used to use.
Okay, that doesn't sound very practical. You could actually, skip planets. I mean, if you go fast, but we didn't know. I mean,
if that's how it works, you're fine. Basically, if you bend space-time that way, you're fine. If you bend space-time sideways, you're not fine. Right? You would die if you try to do it that way.
So,
what do you mean?
So it's creating a corridor of space-time where you just stretch it in front of you. So you create instead of bending and clipping, it's a stretching motion of space-time. So you dilute a corridor in front of you, so you can travel along that corridor faster, and you compress it on the side.
I thought it was the other way around, where you compress it in front of you and go through the stuff closer together at the same speed or something. I don't know.
Pretty much. It depends.
I think that's
where
what
you
Star
put your
Trek
energy.
does. I think some article. I haven't read that.
I read a small description. It was not too clear. I don't think they thought that far, exactly what type of space-time bending there is. I mean, it's not like we know what would work in this anyway. But in some forms of it that have been suggested, you would actually be fried.
Okay. So you're saying that if that's the case, you wouldn't be able to move sideways. You wouldn't be able to turn, right? Just not strafe, is what you're saying.
It's hard, So
sure
in GR, you're allowed to play these games. To play these games of bending space-time, if you can create and destroy mass and create negative mass, you're allowed to bend space-time any way you want. Nothing in GR stops you from doing it. Now, in practice, GR doesn't contain any dynamic predictions. So what does that mean? That means GR can tell you how a particular space-time would make you move, but it doesn't tell you, what would happen if that space-time was moving, or if you were forcing it to compress, where would the energy go? Well, to some extent it does. But dynamically creating things like wormhole folds is not really something that we can easily work out. People who work on these things have to run enormous computer simulations, even for something as simple as a black hole binary, right? All these black holes do is spin around each other in a circle, neat and nice, and still the amount of space-time bending that it takes months of supercomputer calculations to work out the final second of that, right? 1 second in real life, months of calculations, because GR is really complicated. So we don't know.
No, and you go.
I imagine they get up to a pretty good clip when they're getting right close to each other, So it's
they're bending space-time and sending this wave out, right? Rippling, but it's still small compared to what the ships in Elite do. If you want to travel faster than light, the bending is much larger.
You need
Much
more
harder
mass
to
than there is in
calculate.
the universe.
You need negative mass. That's even worse. We don't even know if negative mass exists. I think by the latest optimal warp drive designs, you still need about 1 Jupiter mass of negative mass.
Whoopsie.
Yeah.
Wait, do you have warp drive designs?
Yeah, I mean, of course we work on them. You have to work out these things.
What else are you going to do on the lunch break?
NASA has a division working on this.
Right.
Is that
I mean,
why?
someone's got to do it, and who's going to do it?
Yeah, no, of course. That's a good reason. But we still don't know what negative mass is.
No, we don't even know if it can exist. I mean, accelerated expansion is kind of giving us hope that it might be a thing, but we don't have a proof that it exists in real life. You know Mass Effect? In Mass Effect, their science is really well worked out. That's a good example of sci-fi again.
Is it?
Yeah, there's a specific material. When you pass a current through it, it increases its mass. And if you have that, you can do all sorts of fun space-time warping things.
Didn't they say in game that it decreases mass and so they can travel at the speed of light?
Yeah, with the how do you call them? The beacons. You can still go faster. What are they called? You know, the things shaped like music.
Yeah.
Right.
The gates, the things,
You know what I mean?
Yeah, the jump gates or whatever.
Mm-hmm.
Yeah, so they still go faster than light.
Well, having both would also be pretty handy, wouldn't it? Because once you get up to those speeds, I'm wondering if conservation of momentum and speed are two different things or not. Like, I would compare it to like if you're spinning on a merry-go-round and you move to the outside, it slows down. So what happens if you get up to speed and then somehow magically increase your mass like that? Would you slow down or would you maintain
slow down?
Speed?
Yeah, you'd slow down.
Oh, okay.
Slow down. But if you decrease your mass, you'd accelerate. That's basically what they use. If you accelerate while your mass is high, and then you decrease your mass by not passing current through, and suddenly you get a huge boost.
I'm told the things in the Mass Effect game are called mass relays.
Mass relays,
Yeah.
That's right.
Yeah, indeed.
You should all know that.
I know. I'm actually.
I'm
actually
17.
decided
I
to-
wasn't born early enough for that. Don't blame me.
You were just old enough for Mass Effect.
Yes, but I didn't have a. Okay, fine.
To be fair, I just recently to start Andromeda.
I still haven't. Too many
Yeah,
bad reviews.
I know, but
I've seen funny videos of it. That's all I've seen.
I'm not sure about the science of that, so I can't really comment on how accurate it is compared to the first one. But anyway, we have another question which I left it near after the others because it may result in a long discussion, but maybe not. Let me just find it.
I'm sorry, Nightfall. You're cutting out just a little bit. I think.
Sorry, I'll talk closer to the mic. Because I was told that my set correct.
Still happening.
Checking. Can you hear me?
Yeah, it's when you
Testing.
when you kind of trail off a bit, it kind of cuts out.
Yeah.
Okay, let me see if I can. Did it happen before?
Yeah, it's
Just
been
now.
happening. Just try to go in. If you go in the Discord settings, you can manually turn down the minimum
Yeah,
threshold.
no. I'm doing it on my other voice meter testing. You should have told me before.
Well, I mean, it was an interesting conversation. So.
Really. I'm just tweaking the setting, guys. Just a second. Anyway, let's hope that this will happen again. I will try to be closer to the mic. So I had this other question from Kenny, one of our DJs, Drunken Wolf. I'm not sure if he's listening now, but I'm going to take his question anyway. And that is, does the CMB support any specific theories on how the universe was created? Now, this is a loaded question because we don't know if it was created, but what do you think? I mean, do you think that CMB can help figuring out, we know that it is a proof of the Big Bang, but in addition to that, is there any specific prediction that we can make based on the CMB about the nature of the Big Bang?
Well, that's very related to what you asked me earlier with what can we predict about the future from the CMB. So it's the same situation. As long as your preferred model of physics can predict the CMB, it's permitted. And currently we have more than one. These models have things in common, like they all had a Big Bang. The Big Bang doesn't necessarily refer to the singularity, by the way. That's a bit of a misconception. The Big Bang just means that it all came from a very dense point. It doesn't have to be infinitely dense. The Big Bang in a Big Bounce scenario, the point of expansion is still a Big Bang in that sense.
So the Big Bang is not an actual bang. So that we're clear.
I don't know, was there sound? Probably not. It was probably loud, I don't know.
It's just just like a balloon quickly expanding.
The Big Bang was made up to make fun of it. You know that. Calling it the Big Bang theory was a way to make fun of it, made by a detractor when the model was first conceived. So they didn't like it.
Oh, like
Jokes
the
on
Schrödinger's
him.
cat. It's the same.
No, the Schrödinger's cat was quantum mechanical irony by Schrödinger.
Yeah, it wasn't actually.
That's even worse because
it was a way
he's
to
the
make fun of the theory.
yeah,
I was reading
Schrödinger
that.
was taking the piss of quantum mechanics when he came up with the Schrödinger's cat. It was never supposed to be real. It was a piss take that something like a cat would never be quantum. The cat is not quantum. It's
Finally.
dead or alive. No.
Uses it when they try to explain quantum mechanics.
Yeah, and that's really sad, actually. And it's in fiction everywhere.
Yeah, because it's easy to picture, but
It's atoms do it, cats don't. The piss take was about where's the limit. Like, surely you can't go as far as a cat. And he was right, you can't go as far as a cat.
Of atoms.
Yeah, but they're not quantum. There is a limit called the Fermi limit. Somewhere in between, things stop being quantum. A human is never quantum. You're made of too much stuff. That's a discussion for another time. I get heated about quantum mechanics. I used to teach quantum mechanics.
Okay, well,
So
sorry, go ahead.
So back to the Big Bang being a bang, though. Like, I imagine at the densities that they had, theoretically, if it all came from a relatively compact point, at those densities.
Sorry, Thor. Can I stop you a second because we're going to go back to that? But
Oh, okay. No worries.
I was baking up this joke from before. I don't want to change the topic before I have a chance to
Go
make
on,
it.
say your joke.
Yeah, okay. Joke, but I've read a very scientific paper a few weeks ago about the fact that since you mentioned cats and quantum mechanics,
Oh god.
We all know that quantum mechanics is about the small things. The smaller you get, the more into the business of quantum mechanics you get. We also know that the smaller the cat is, the cuter it is. That is also
true.
That is also true. So, is it true that basically a quantum cat, it would get smaller and smaller, at the same time it would get cuter and cuter until it disappears from view?
Oh.
I mean, you would reach, how do you call it in quantum mechanics, the edge of...
The cat cuteness horizon.
Exactly. I mean, it's like... So if you shrink a cat, it will become cuter and cuter exponentially until it disappears from view.
Yeah.
So it is possible to make a quantum cat, according to this paper I read.
Black hole of cuteness!
I'm afraid that level of cuteness might destroy the universe.
That's why.
But how many atoms do you need to make a cat? Is 3 atoms a cat if they're made in a cat head shape? That's the real question.
It's the cat atom. It's an actual atom.
There's no cat element.
No, it's not an atom, it's a catum.
Oh.
Okay, and that was the break from actual serious science. Now Thor can proceed with actual serious stuff. Go ahead.
Okay, so back to the Big Bang being a bang. Presumably at some point in the process of expansion, which can't have been for terribly long, but presumably there was enough density for things like sound waves to be bouncing around.
Oh yeah, for sure.
And if so,
Yeah,
it would have
for a
been
long time, actually.
exceedingly loud indeed, I would imagine.
Loud, but you really get into how do you define sound at that point.
Well, we're back to the tree in the woods and nobody hearing it, aren't we?
Yeah, that's one part of it. There was definitely no one probably vibrating, but it wasn't made of. So, like waves on the sea are vibrations and they propagate, but you wouldn't call them sound. They're waves, water waves. They're not, just because they're the same kind of waves doesn't make them sound. So it's kind of a philosophical question. There were waves propagating through this thing, like waves propagate in water. But if you can call them sound, I'm not sure.
If I can just interject as well, I think another aspect that would happen would be similarly to how you can't hear a sound through a wall. The denser the material is, I believe, the quicker it disperses through it, and so simply because of the fact that it would be so dense, I personally don't see that sound would actually technically propagate, and so I actually wouldn't say it's. Well, it would be exceedingly loud, but I wouldn't say it's relatively huge.
Not at first. Not at first. It wouldn't propagate at first. You're right. It would dissipate too fast. But as it cools and it reaches kind of the temperature and density of the sun, then you would start to really see propagation. And we see them in the CMB, actually. From the time that sound waves became a thing to the time that the CMB fog lifted, there was a time where these waves propagated, and you see them. We call them baryonic acoustic oscillations, and they're in the CMB. There's like a preferred scale, which is how far these waves have traveled. That's actually one of the ways we can measure exactly how dense it is at the time of the CMB.
Ah.
So we do see them. It was oscillating. It's an oscillating plasma, not air.
Mm-hmm.
That's cool.
Yep.
Okay. Well, yeah, the thing is, I sometimes end up in debates with people who are not as science savvy as elite players on average. And when somehow the discussion goes into the Big Bang, what the question that I always hear is, yeah, but what was before of it? Do you have, of course we can't answer this question because it's invalid, but do you have, because maybe it happened to some of our listeners as well, how can you, is there a way that you advise people to try and make others understand that you can't really ask what was before time itself? How can you put it in simple terms so that somehow someone who doesn't know much doesn't just, you don't fuck their head because
if it's someone that doesn't know much and they're quite adversarial about it, I mean, the honest answer is that we don't know. We have absolutely no idea. But it's more complicated than that, right? Because after the CMB, we can see stuff. So that's secure. And even after the CMB, we get all of this big history of things forming and assembling, different epochs and such and such. Before the CMB, which was about 300,000 years after the Big Bang, before then, of course, it gets denser and denser and denser. But actually, apart from the first 4 minutes, all of that phase is physics that we know. So it's not completely crazy physics either. Only the first 4 minutes you get into the range of things we can't do in labs, things that are a bit funky, like how the atoms formed from primordial energy, that kind of thing. But everything after the first 4 minutes is actually physics that's well tested. We know how material of that temperature and density would behave. It's actually been tested. It's well known.
Yeah,
So you don't need to know what came in the first 4 minutes. The theory of the Big Bang is just that there was something. We can't really say what was in a period where we don't know what the laws of physics were, because we predict the laws of physics themselves wouldn't even apply at this kind of energies of the first 4 minutes.
The Big Bang itself is defined as a singularity, right?
Not really. It's not really defined like that. The Big Bang Theory just means it all came from one place.
Yeah, but
place in a loose sense.
This place is where physics breaks down as we know it.
As far as we know, because of the contradictions between GR and quantum mechanics, we don't even know if singularities can really exist. Because in quantum mechanics, everything has a minimum size. The singularity in GR is infinitely small. So these things immediately are kind of contradictory. So what would it actually be if you had quantum general relativity? What even is a singularity? We don't know because we haven't tested it and we don't have a theory for it. But we don't need to know. It's okay to admit that we don't know what it looked like. We don't really.
It might not even be possible to know simply because you can't see that far. Like,
we can test it in other places, hopefully. If you can construct like a particle accelerator to go to even higher energy, we can know how matter actually behaves and get closer and closer to it. And maybe have a theory like quantum gravity, what people are working on, like a theory of everything. And that would make more, believable predictions. But currently, there was some sort of singularity. We don't really know what it was. We don't really know what came before.
So we just use this term singularity to define things that currently we don't know about.
A singularity is a prediction of general relativity.
Yeah, in which basically it's where laws predicted by relativity break down.
No, they're okay with it. The laws of general relativity have singularities as things that can exist.
Yeah, like black holes. Black holes are singularities.
They're singularities and they're protected by an event. And as Stephen Hawking discovered, they evaporate over time. And as I think Penrose discovered... I lost my train of thought.
It's my fault. I am just going off on a tangent here, trying to look smarter than I am, but obviously I'm not. So I'll just let you talk.
Singularities, do they exist? What are they really? The honest answer is we don't know. Until we can unify general relativity and quantum mechanics, no one can say confidently that they know what a singularity is. According to GR, it's just infinitely dense and infinitely small. Can it actually happen? How does it form? We don't know.
Now here's a question. Can a black hole even happen? Do we even know the answer to that? Because that's kind of, I don't know.
There was some doubt, like how the process of collapse into a black hole would actually happen. I think since LIGO's detection of black hole collision, that's really the nail in the coffin. Like, black holes definitely exist. And they are what we think they are. Because we predicted the shape of the LIGO signals exactly, even before we detected them. So it was a huge moment of, science coming true. Our predictions were all verified.
So just to give a bit of context, LIGO is the, just in case some of the listeners don't know, is this huge thing that has been built where in the US, I think, no?
There's two in the US, and now they've added one in Europe, Virgo.
Yeah, there's one in Louisiana, and there's one in, I think, Arizona or something.
Yeah.
And they detect gravitational waves. So.
And Livingston, both in the US, stands for Laser Interferometer Gravitational Wave Observatory.
Yeah, so basically, they detect gravitational waves from huge collisions of neutron stars and black holes, right?
Yeah, mostly mostly intermediate mass black hole. Sorry, and one neutron star collision.
So we don't need light in that case. We just use gravity to detect and identify things, and gravity ignores fogs, clouds. They just go through it. So you can't really stop gravity, right?
Yeah, that's true. Gravitational waves, in theory, they could travel to your primordial. They could allow you to see slightly further. Although we are very far from that in terms of technology.
Well, I don't know.
We can only detect the loudest things, not like a super faint background that gas was doing by vibrating slightly,
Could you use... Well, no, I guess you can't, otherwise someone would have done it already. But if you can detect collisions of black holes, which I assume create, a huge amount of I guess, gravity, I assume, would it be far-fetched to try and detect the gravity of what happened at the Big Bang? Because I assume that in the Big Bang, a lot of big stuff happened. There was a lot of noise, probably much, much bigger than two black holes colliding. We're talking about the entire universe expanding.
According to our simplest model, go on.
I would guess probably no, because I think of it like dropping a pebble in a three-dimensional pond.
Well, I said if it was possible, it would have been.
Well, yeah. So the ripple's out beyond us already.
No, because the ripples from far away would only reach us now.
Oh.
It's like the CMB. It's the same situation, but according to our simplest model that explains the CMB, because it's the one that we like the most. It has actually the fewest assumptions in it. It's the model of lambda CDM plus inflation. In the model of inflation, in the very first microseconds or less of the universe, all of space-time became ultra-stretched, probably by something called the Higgs decay, which I will not go into details of. But space-time goes from being super dense to being super stretched and flat in the first microseconds or nanoseconds. And because of that stretching, all the noise and vibration of energy creation has been stretched too with space-time when the space-time was stretched. So it's become unobservable. It's been stretched to oblivion.
Okay.
By something like 10 with 60 zeros after it, or some ridiculous number of stretching.
Right.
Oof.
Well, because it turns out this Higgs inflation has two very neat properties. It expands space-time when it decays, and it produces a shit ton of energy, which can then become matter. So that's why it's like the easiest explanation. It has these conspicuous properties that if only we had a Higgs decay, we'd have a huge space-time to play in, and we'd have matter.
I mean, that sounds slightly dangerous to create in a lab.
It's not really related to the Higgs particle. Well, it kind of is.
It's just called like that because of reasons.
Because it travels on the same field, but that field used to be different. It collapsed into the current state. That's why we have Higgs particles today. And the same destruction of that field is what created inflation and gave us all the matter. That's the simple model that particle physicists and inflation researchers work with. Mostly.
Yeah, I guess that if we want to go, it's going to go quite complex in terms of...
Inflation's hard because it's not very observable. We just like this model because it's relatively simple compared to the rest.
Before we go too far ahead, I'm just going to take this question from Sleeping Insects. Nice nick, a bit creepy, but okay. I mean, you mentioned 4 minutes earlier. I believe that it's when you were talking about that we know exactly what happened after 4 minutes or something, right?
Yeah.
He is asking, how did we calculate so precisely? Because 4 minutes is nothing in 13 billion years. How did we calculate time signatures during those first moments? I mean, is it just by again with light and with what the CMB radiates?
Yeah. So you have your model, and then you have to make sure it fits all the things that we see, and then you can extrapolate it back. We know that if you start with matter that's infinitely hot, say in this Higgs, whatever it's called, I've forgotten the word. Well, even if you start with matter that's infinitely dense and it has a lot of space to cool in, it will take about 4 minutes for it to be done with coagulating into atoms and the particles we see today. That's about the time it takes if you let it cool at the rate that it wants to.
4 minutes, and that's just, you just tested it. I mean, that is what it is. Not a
Well, it's a prediction. We don't really know. It's like after the first 4 minutes, it would be cool enough that we trust our models of what matter would do. Before the first 4 minutes, it does weird things like creating atoms, creating quarks, and so on.
It is still more or less an estimate.
It's an estimate. Okay. Well, it's a good estimate. It's a reasonably good estimate. It's not like it's 4 minutes and we know exactly how long ago that was 4 minutes. We don't know that. We don't know how long ago it was up to 4 minutes. It's backwards. We know it would take 4 minutes to go from infinitely hot in an expanding universe to something that's reasonable in terms of physics.
Okay. Well, moving on, because we're getting tons of questions, guys. That's good to hear, because if we see there is lots of in this kind of talk, we are going to actually make this an actual weekly thing. This is a bit of a test run to see how much people are listening in and interested in this kind of talk. So keep the questions coming. If we don't have time enough today, we will save them from next time. But in the meantime, there is another question concerning the Large Hadron Collider from DJ Creep, I guess. Yeah, the DJ Creep. He would like to ask, what are your thoughts on the plans to build a larger Hadron Collider? I hope that's not going to be the name. Larger Hadron Collider. It's going to be the even larger Hadron Collider.
LHC is the same. That's a terrible name.
Yeah, it would be, I don't know, very large, VLHC.
Currently it's called the Future Hadron Collider, but I assume that's a working title.
Well, scientists are not very good with names.
We are not.
So I wouldn't
You don't want to know the abbreviation come up with for stupid projects.
I wouldn't be surprised if that be a thing. But so there is this plan, right, to build a larger version of the LHC. What do you hope that we could learn from it, or what do scientists in general hope that we can learn from it?
That's really going into particle theory.
Yeah, I know it's not your field. It's just that I took this question. I'm just asking you. I know it's not cosmology.
Particle physics is something I should remember from my degree. Let's see, particle physics. Particle physics. Quantum field theory.
We had a physicist in the audience earlier. I'm not sure if he's still tuned in.
I think I can summarize vaguely what they hope to achieve. Basically, the more energy you can put into particles, the more interesting things they will do if you blow them up. Okay, so you accelerate particles to give them lots of energy, and at the moment of collision, their mass becomes energy. It's E equals mc squared. All mass is also energy. So you turn your mass into energy, and then all this energy can choose to coagulate into a different type of mass, and that's what a collidron does. Collidron. A large a hadron collider does.
It's a good name though. Collidron.
Collidron is a good name.
That.
They could use royalties. So that's basically how it works. You take your particles, you smash them into energy, you let them decay into any form of matter that they prefer after that. And that's how you find lots of particles, right? But say that some particles that existed early on had really, really large masses, but since then they've all decayed, like maybe particles in supersymmetry or the such. If you wanted to recreate them on Earth, you have to get into one place enough energy that would create them, enough that would become mass and create that stable particle that we don't see otherwise. And that's why we build larger and larger collidrons, because if we accelerate particles more, they gain energy, and you turn that energy into pure energy that can then decay into more interesting heavy particles. So they're hoping to find heavy particles like this that are predicted by a whole range of models, especially supersymmetry, which is still a huge candidate to explain everything.
Sorry, go ahead.
When you're talking about particles that could have decayed since then, does that include, like, for instance, 5 quark particles, like I can't remember what the technical name is for them, but more than 3 quarks? Like, sort of stuff like that, or is that something else that I'm thinking of?
I don't know that one in particular, but it's the right kind of thing. It's assemblies of subparticles that live for a long time, but not forever. Mm-hmm. I think even protons have a lifetime. You can stay a proton forever. So if those particles that used to exist back then, maybe in the first 4 minutes, but then they decayed really quickly, we would have never seen them. So we want to know if they exist, because we've predicted exactly what should exist. It's just we need energy to make them.
Yeah, I'm sorry we dragged you into particle physics, which is not your field.
No, it's good.
But of course, you are still more prepared than most of us. But we're going back to the actual cosmos, because we have another question from earlier, still from SRM. He's wondering if gravity waves, we were talking about the LIGO earlier, if the gravity waves aren't affected by anything. And that and if these waves can be actually called gravity, or and if they themselves are affected by gravity. I mean, can there be some sort of gravityception where you need to take into account gravity to calculate gravity?
Yes.
Okay.
That's the short answer. Absolutely. So in general relativity, it's not only mass that curves space-time, energy curves space-time too. And these waves, even though they don't carry mass, they still carry energy. So they curve space-time under their own energy. A bit like when anything travels on space-time, it curves it, and they do it too. It's very much like ripples on a pond. They self-propagate. They affect what's next to them, and they keep moving in one direction.
So LIGO has to take into account everything that's in between itself and the event.
Well, not really, because like the ripples pond, if you have very big ripples that are basically just flat, like a flat line by the time they reach the shore, if you just have a bit of like stones or really small things, they will not stop your overall wave. Basically, they don't have the right size or the right wavelength to interfere with them. So if something really small cannot stop a very big wave, that's a good general rule. So
it can't stop, but it can.
Even something like the Earth basically has no effect on something the size of a gravitational wave. By the time it reaches us, it's very much straight. It's not going round the center anymore. It looks really flat by the time it reaches us.
So it doesn't even interfere with it in any way.
Well, in theory it does, but it's a very, very...
I guess that's why we needed black holes to collide to make it work, right? Because that's the only thing that puts off a big enough wave that's detectable and won't get fuzzed up by all this stuff in between, right?
Pretty much, yeah. And it's the only thing that our detectors are big enough to pick up. For example, mergers of supermassive black holes, like Sage Star, when those merge, they would make gravitational waves too, of course, but LIGO cannot see those yet, because they're of the wrong frequency. And with the length of the arms that LIGO has, can't see those. And that's why we're planning a mission to detect gravitational waves in space, which is LISA, I think it's called.
God, the positional accuracy they need for those satellites, though. Oof.
Well, they just have to know how they move. They'll move pretty much the same every day, so I guess after a few years they'll know exactly how they move.
Imagine just the full LIGO building in orbit, just the entire thing.
Yeah, but it's easier because you don't have to keep your tubes being a vacuum. You already have a vacuum.
That's
so
you
don't need the energy for that. You don't need to line up your tube so that the Earth doesn't bend. Space is just empty. Nothing's going to bend your light. In a way, I think it's easier.
Talking about black holes, Kenny linked another article. I believe that this is not new, right? It's from last year. I think you actually seen this, Sarah. The fact that there are some, I believe, physicists that say that black holes may not exist at all. Because I'm just quoting from the article here that there has never been a direct evidence of a black hole.
I disagree. Already, first line.
Yeah, I'm sure you do. This is from dailygalaxy.com, and the funny thing is, as a picture of a black hole, they use an elite screenshot. This is not an elite related website. This is a science website that apparently is using elite screenshots for their science article. So I don't know, but anyway, this article is saying that this physicist says that there are objects that general relativity would predict are black holes, but we don't have any direct evidence of it.
You have to have a pretty narrow mind of what positive evidence is. Then, if that's really the argument, if you see lots of stars moving around something heavy that you can't see, like at the center of our own galaxy, these stars that move, and we see them move over the years, they're moving around something very heavy in an orbit, and it's something at the center. We can calculate how heavy it is by how much is bending these stars, and it's something dark. So you have something very heavy and dark at the center of the galaxy, but that's not direct evidence enough. I mean, how do you even define evidence then?
Well,
that's what I would ask him.
I'm just skimming through this article. Of course, you're listening in the radio, so you can't really see it, but there is this article posted late December last year. Physicist named George Chaplin, I'm not sure how to pronounce the surname. But back in 2005, he stated that it's a near certainty that black holes don't exist. I'm not sure what he means by near certainty. And that he is suggesting another model that he's calling dark energy stars.
Yeah, I've heard of those.
You heard of that?
There's a few versions floating around.
Okay.
From what I understood last time I caught up on this, they're saying that black holes could exist in GR, but by the process by which a star dies, you could never form one. So that's their main opposition. We haven't seen black holes being formed, and they think because of the pressure involved by trying to make one, you could never actually get through the process of successfully making one. That was their main argument, as far as I know.
But it's fringe at this point.
If you have something called a dark energy star, that's the same mass, it's also dark, it bends the trajectory of stars in exactly the same way. Call it whatever you want. I want to call it a black hole.
So basically you're saying that if it looks like a duck and it sounds like a duck, it's probably a duck.
Yeah. And I'm still waiting to see their prediction on the shape of the oscillation of gravitational waves from anything other than a black hole, because they haven't predicted those. And even if they predicted them now, they had to predict them before we observed them. Otherwise, it doesn't count.
Well, it's just two dark energy neutron stars colliding.
Dark energy neutron stars? What does that even mean? How could dark energy...
It means black hole, but they just don't want to admit it.
I don't think you can just put random words that sound spacey and have new things.
No, I agree. I honestly, I believe I saw something on the internet of us. They've calculated a star moving at something stupid like 20% the speed of light in orbit around Sagittarius A star. Which just is mind-boggling. Like a freaking star moving that fast is just... Think of the
energy. Can you imagine in Elite if you came across that?
I want to see that.
Whoosh! The star just zooms past.
I mean, we got planets to do that, but you know.
Yeah. So there's a lot of articles on media, not only online, but mainly online, that may not be entirely accurate. And sometimes if the reader doesn't have a grasp on how or what the scientific standards are for proof, evidence, headlines tend to like huge titles, sensationalist titles to grab the attention. But
and I think sadly sometimes scientists who come up with something, they can be really proud, when they talk to the media, they can, instead of saying this model could also explain this, it's an interesting alternative which we should explore, maybe they will say something like black holes don't exist, because by bashing the opponent model they can make their discovery even more interesting than it. I guess scientists do tend to get attached to the things that they discover personally. And unless you have peer review and you get the opinion of many scientists, you can't really, be objective. It's good to have many opinions in science.
Yeah, it's just that sometimes, if you're not a scientist, you don't really know what to believe. If you read an article on a science website or a science magazine, you tend to believe it because you don't really have the tools to realize, is the journalist being fair? Is this what actually the scientist reported? Is the scientist being fair with what he has actually discovered? I assume that the only way to figure things out for sure are to go and read actual papers.
Yeah, that's why we have such a difficult peer review.
Yeah, but papers are not exactly easy to understand for someone who is not a scientist. They're full of jargon and numbers and things.
Yeah, no, I agree. Well, I would say they have to be, because they can't be written using any ambiguous words like very big. You might want to say to the public, this thing we found is very big, but you would never put that in a paper. I mean, that's not accurate. What does that even mean?
Yeah, no, of course. But at least we do have outreach.
I agree with you. I think scientists should do a better job of presenting their own work. At the same time, just because you're a good scientist doesn't mean you're a good speaker.
Well, that's the
Or
thing,
even
and you go to school for stuff, right? You learn certain terms and stuff, and everyone around you in your workplace is using this stuff, so you kind of maybe lose track of how normal people talk about stuff.
Yeah, I've got that issue. My entire life, well, obviously I'm 17, so currently I'm still in Scottish high school. And so my entire life revolves around the physics department. And so whenever I'm talking to someone outside of that on something I find interesting, I'm always the guy who seems insane. And to be fair,
you are,
but it is very difficult to get a point across without analogies. Like what you were saying about, earlier about how it's difficult to explain how it's invalid to ask what was before the Big Bang. The only way I was able to actually explain that was through what Stephen Hawking said in I think it was Brief Answers, that the most recent one. What he said was that asking that question is like asking where the edge of the Earth is. In that sense, so it's very difficult.
Yeah, no,
I don't like that one. That one specifically.
I've heard,
but yeah, it's a nonsense question.
I've heard like asking what's north of the North Pole.
Exactly.
Yeah, it's a lot like that. What's north of the North Pole?
Yeah.
Well, you're at the North Pole.
Exactly. You're using the North Pole.
It's relative from that point on.
Yeah.
It's an invalid question, but the human mind is not built to understand something out of time. So it is only natural to want to know what was before something, even if that's not a thing.
When it comes to thinking about supposedly illogical questions, or as we put them, invalid questions, human beings, when we've got something that disagrees with our normal, every day-to-day, logical, so-called experiences, we have the worst failsafe ever. It's you might know it. It's called emotion. Whenever someone is definitively proved wrong, you'll notice they'll get angry, and so that's one of the issues with human beings that we need to overcome for better science. It's very difficult to do.
Yeah, and being a scientist is like learning.
For science, yes,
definitely.
Your entire career is about disprove others and being disproven yourself.
Oh, you don't have a choice if you become a scientist, because the things you come up with will be wrong 80% of the time.
Eventually.
If you can't take disappointment in yourself, you cannot be a scientist. Because
go ahead.
It's very rare to find something that works, just in general.
Isn't that basically the description of the scientific method, is guessing and trying to prove yourself wrong?
Yeah. Pretty much. So you have a nice hypothesis, then you try to prove yourself wrong, and usually you succeed. And then
you still want to win an award, so you try to be right.
Figure out everything wrong, so that you can, by process of elimination, find out what is right, what it must be.
Yeah, pretty much. I mean, once you're used to coming up with things and disproving them, and you find some proven, you start thinking, maybe I should tell the people about this.
Mm-hmm.
And then they will prove you wrong. And then if they don't prove you wrong, then you write a paper. And then you repeat this forever.
Yeah.
It's a very disappointment-heavy job.
But you still do it, right?
Oh, I love it.
Speaking of which, we are getting near the end. But I believe that you received some private questions, Sarah. I'm not sure if it was today or...
I got a few. Most of them were about quasars. Maybe we can have a quasar day.
Yeah, I don't think we have time to go into quasars today, but we can definitely do that. I mean, I would also like to make to host a show about time itself. I'm not sure if that's something you're comfortable talking about.
Jeez, I can brush up.
You know, the actual
the concept of time in physics.
Yeah. Again,
you have time.
We briefly touched time, and it is something that's really hard to even visualize in your head. I would like to have a show about that. And I was wondering if people listening in now are interested. If you guys are, please drop us a line on the Distant Radio 3305 chat. That's just my idea, though. If that you would like Dr. Bosman to discuss with us, please let us know, and we will see what we can do about.
Yeah, I think especially time in the context of cosmology is very interesting. Like time distortions, space distortions, inflation, and all that.
Yeah. But again, what was the question that you received? Because I think it was a bit philosophical in nature, right?
Yeah, I also got a very long question, which boils down to, why should we try to understand the cosmos? Is it the journey of the heart? Is it spiritual purpose?
Don't. I mean,
it's a fair question.
It is.
Well, since when do humans need a reason and anything? Yes, as far as I'm concerned, curiosity is the most human quality ever.
Yeah.
You see something you don't understand, and you're like, I want to understand that thing. You see like a mountain, and you're like, I want to climb that mountain.
You see something fluttering in a bush, and you're like, what the hell is that? You know?
Well, I'm going to be honest. I don't have the fitness to do that. I'd rather use my mind.
Well, it's just an extension of it.
Here's a concept. I want to understand it.
Well, the thing is, I understand what you're saying, but now we're reaching the point where we're trying to understand things that we don't even see, or we don't even think it exists. I mean, I agree with you. I personally believe that knowledge is its own reward, because you can't really stop pursuing knowledge, because that's when your civilization dies. Even if it's something that you say, but there's problems closer to Earth that need solving. Why do you care about quasars?
We do not get a lot of funding compared to medicine. Don't worry.
Sure you don't, but some people would even like to remove that little that you have. But my personal opinion is that there is no excuse for not trying to learn more. Sadly, I'm not smart enough to contribute much in that regard, but luckily some people like you are, and I think we are all grateful that you are underpaid to do this kind of difficult job. Not everyone is willing to do that. So that's a great thing, because it's mainly passion that drives science at this point.
I'm still amazed people are ready to pay me to do what I do. I mean,
okay,
I find it super pay you to do your hobby. I'll be doing this anyway.
Right?
It's pretty lucky.
Well, you shouldn't tell them. Wait a second. Wait a second, though. I think they know, because that is literally the reason why they can manage to underpay you, because they know you would do it anyway.
Oh yeah, I have no doubt. That's why they pay us as little as possible.
When it comes to,
I mean, maybe you're not that smart then.
I have to be pretty.
I'm joking.
I have to be pretty
But-
stupid to not take 5 times
Oh,
much of
well,
the same.
I'm saying, look, guys, we need a raise.
Or what? I mean, they'll find out the people who want to do this.
Fair
It's
enough.
not, you know, it's still oversubscribed, like
Yeah, I
20
would like
to
to
1.
think really, really brilliant scientists are not that common. They can't just replace someone that just like that. They go on what, LinkedIn and Google phenomenal astrophysicist and just hire anyone.
I think it's oversubscribed about 10 to 20 to 1. So if someone who's slightly worse than you does the job, you know, it's a balance. Plus, in science, it's really hard to know who's good. It's not like you can sit a test anymore because no one knows the answers to what you're trying to solve.
Is it because you're good or because you're lucky?
A bit of both, I guess.
Yeah.
I don't know. I think beyond even as early as PhD students, when we select PhD students, it's not even on marks anymore at that point. There's like something that makes you see they're going to work hard and maybe they'll find something one day. Being willing to work hard is something more important than marks beyond the threshold.
You know, I actually like that. Like, I appreciate that mindset in the scientific community because, yeah, you know, someone who's willing to put in like that elbow grease, like stay up all night trying to get that homework done is, you know, someone who's like doing the hard work is far more likely to go out there and continue doing that than someone who just kind of floats through getting straight A's, right?
Yeah. Plus, the ability to sit tests really becomes useless if no one knows the answers. It's good that you can cram. It's good that you can store knowledge. That doesn't really tell me if you can apply it to new things. You have to actually try. That's what the PhD training is for.
So in your case, the reason you do this is because it's fun. Or do you have any more spiritual reason to do it? Whatever that means.
I just really like it. I think high redshift objects. I mean, I would be reading on the latest things I find out about them anyway. You know, it's just so cool that I get to like choose which one they observe.
Do you have a noble purpose on this? Are you trying to further mankind's presence in the galaxy? Are you trying to make sure that we stay on track and we don't lag behind any other potential other civilization out there? Would you like to see humanity slowly develop into a more scientific mindset globally, so that we all learn to analyze things following the scientific method, not only in science, but to have that mindset by default? Do you have any of those things, or you just?
Yeah, I do. And actually, I think most scientists don't. I think most of my colleagues really do it because they find it fun, and that's all the reason they need. And that's probably why some of them are much more productive than me. I think it's very important to spread knowledge about these things too. So to me personally, doing as much outreach as I can, whether with books or on the radio or on shows or in live meetings with people, I think talking about the latest things we find is really important so that people are aware that science works, you know, and that it should be inspiring. I remember when I was learning about things, I used to think about them nonstop. How does a neutron star look like? You know, then we discovered that neutron stars have earthquakes, and it was the coolest thing ever. I think just the sense of cool will keep people wanting to explore. So maybe the people who are even better than me at doing it will get into the career because they know about it.
I'd like to expand on that. I've actually had something, again in reference to my age, because of the fact that I am quite young. I'm about to start uni, hopefully just at the end of this year. I've had that for quite a long time, and it's still very explicit in my mind when it comes to wanting to study physics, and specifically for me astrophysics. It's just the feeling of, for me, it's just the feeling of obligation to figure it out. That's what drives me. It's just the unknown that I find. I can't tell if it's either terrifying or if it's so intriguing that I'm blinded by it. That's what drives me towards that.
Yeah, I totally get that. If I can give you one advice, it's maybe a bit early, but if you want to do a career in research, try to do summer jobs, summer research placements as early as you can, because you won't know what the job is actually like before you actually try it in a lab with people. All the courses you learn are going to be very useful to accumulate knowledge, but you won't know if you actually like exploring and doing things yourself until you try it. It's like a friend said once. It's like, I really like watching the TV show of physics. I really like learning all the episodes, all the chapters. It's really cool. But I won't know if I like writing it until I actually try. And it's very much like that. Just because you enjoy watching something, making it is very different from learning. So try it hands-on. You'll know if you find it fun.
Well, that's some good advice. I think it applies to all sorts of professions, not just science. But that is indeed good advice. We are almost out of time, but we have time for one more question. I'd like to remind everyone to please keep the chat channels clear. If you have questions, post them in the interview questions channel, not in the chatter, and leave the chatter in the chatter channel. Please, that just makes it easier, so that the host won't miss questions. I hope I haven't missed any today. If I have, that will be answered next time. But yeah, while we are on the topic of, in a sense, outreaching, because we're talking about bringing science to the people, so that everyone knows what you guys do in your secret labs, spending taxpayers' money by, I don't know, building quantum cats or stuff like that, while people starve in the street. But Thaddeus is wondering, how do you deal with emotion, in the sense that can they interfere with science and the scientific method? And if there is, and if scientists just find ways to mitigate that. I think this does not only apply, having the ability to be objective with your own theories, as you mentioned earlier, but also about the fact that lately there is, in the Western world, a sort of anti-science wave that's been propagating. He is mentioning stuff like global warming denial, flat earthers. I mean, I mentioned them, although obviously they are barely worth mentioning, because I don't believe they actually believe that themselves. But there may be some more vulnerable minds out there that may be falling prey of those, just those frauds. And you guys work hard, and you have to face those charlatans every day. And
thankfully not.
Well, no, in the sense that all they have to do is to just make a few videos and write down a nice speech, and being able to talk, have charisma, and they can undo the public reception that may be an actual scientific theory, but by someone who is maybe, as you said, not as good as at talking. That may influence funding, because if that reaches the government, I don't want to mention any specific government currently
Italy
on the planet. I mean, it starts
the obvious one.
I mean, it starts with A, but I mean, there are some countries that,
Brazil.
That mentality, which personally I think is dangerous, may reach government levels, and that in turn influences funding So
If it does, I'm buying a pitchfork.
well, it's really happening.
I'll get the
in a
torches.
sense. Do you have a way to deal with that? Do you just keep going and do your job, and you just accept what it is? Or do you have a way not to get defensive?
That's tricky. Wait, what was the question? Because the first part was about dealing with emotion. Perhaps.
Yeah, I mean, it was a question, but I assume that if you're passionate about something, and then you witness frauds that just spew bullshit all day and they undermine your work, you get. I mean, normally one.
I mean, they mostly make me laugh. These guys. I don't. I should get upset. I'm upset about the wider following they have, but I can't listen to the things they say and not just laugh at it. I don't think I'm the kind of person who would take them on, like one by one, like one-on-one debate, like some people on YouTube do, and in real life, some people are really good at doing that. Richard Dawkins, Hitchin, they're really good at debunking cracks. I don't think I'm good at doing that. I think what I'm good at is explaining actual science well. So sort of providing the counterweight of actual, content that is accurate and, supported by evidence, explaining exactly what the evidence is and so on. And I think that's my role in this fight. I'm on one side. I'm not on the front lines yelling at idiots because that's not what I'm good at. Not that I would get upset, it's just not what I do. I don't yell at people.
That's fair. I mean, you do what you do best, and you leave the yelling and fighting to people who actually do that. It's fair. It's fair. I think that's the best thing. You mentioned Hitchens. Sadly, he passed away. I miss him because I watched a lot of his videos on YouTube. And yeah, he's great at doing what he was great at doing what he did.
A lot of people are. There's a lot of anti-science debunking going on. I also think you don't even need an in-depth science background to do that. If you have even a moderate science background, you can recognize they're idiots, right? So I should probably do what I'm good at.
Ironically, you would just need to be good at politics, because politicians, obviously they're debating against each other for the good of the country or whatever, or this bill or whatever bill, but they're really good at looking at an opponent's argument and seeing fallacies. And so if you look from a politician who's, well, obviously this isn't an actual thing, but if you were somehow able to find a politician that was non-biased, they would probably be able to look at the fallacies in someone's argument. And so that I think that's what you mean by anyone could sort of pick apart and actually see what bits are based in fact and what aren't, how people manipulate information and other such things.
Yeah, I think it mostly takes common sense and a bit of knowledge. It doesn't take, in-depth knowledge of physics and such. Though it's always more credible when it comes from someone with credentials.
Yeah.
There's plenty of people doing that already. And yeah, politicians. I think there's a few politicians now that are trying to fight idiots with facts. But it's very hard when a fact seems to be something vague in people's minds in politics these days.
Mm-hmm. It's like when people say that gravity is just a theory, whereas the definition of a scientific theory is something based off of extreme evidence. Or, well, not necessarily extreme, but just yeah.
Yeah. That's the thing that personally bothers me: the fact that people use theory in a colloquial sense, and they don't really understand that theory is the best thing you can get in science. Mm-hmm. So yeah. Also, sorry. Anik Haifu mentioned that my voice sometimes goes away. This is why we're using one microphone, Shoba. So it's a bit hard. I'm not a professional at this, so I don't have a professional setup. We'll try to get better next time. We'll re-listen to this stream and check how we sounded. Anyway, we are sadly out of time. It's been 2 hours.
Damn.
Yeah. I hope you guys enjoyed that. I hope also that I got all the questions. If I haven't, just drop a quick note on the interview questions channel after we're done, and we will pick them up next time. Again, as I mentioned before, this is technically a weekly event. If there is enough interest in this, we will find a new topic for next week. Again, assuming that Dr. Sarah Bosman will be available.
I've kept my Wednesdays.
Yeah, she almost missed tonight because she's busy actually working. But we will see what we can do about that. In the meantime, keep the questions coming, the topics coming. And I would like to remind everyone that Commander Shoba has a weekly article on the official Distant Worlds 2 newsletters. There's been 3 of them so far, I believe. And again, that is also a weekly thing. So I advise you, if you haven't, to read them, because they may give you ideas of what to ask. I believe that she touched about star types, black holes, as well as the first one, which was an introduction of what she's going to do. Basically, the idea is to compare Elite to actual real-life universe and find things that are either correct and accurate, that the Stellar Forge did properly, or things that they could be improved upon. That is the idea behind the articles. So again, if you haven't, just have a read of them, and you may find some interesting stuff that we may expand upon during this weekly talk.
And as a final word of shameless self-promotion, if any of you are in the UK, you can meet me in real life. I'll be in Durham on February 21st and in Swindon on April 12th. You can find it on my website.
Yeah,
and the link to your website is?
sarahbosman.co.uk.
Sarahbosman. What was it?
.co.uk.
sarahbosman.co.uk.
I'm sorry, did you say sarahbosman.co.uk?
Yes, I said that.
If you throw that in the
in the links
questions, I can for you.
Yeah. Yes, we'll also newsletter. So you can read her papers actually, if you are into more scientific writing. I believe there is a link to all the papers that she published, right?
Yep.
Cool.
Yes. Not particularly understandable, but yep.
Yeah, if you're not reading the chat, the spelling is, Sarah, S-A-R-A-H, B for Bravo, O for Oscar, S for Sierra, M for Mike, A for
It's
Alpha,
okay, I think they get it.
N for no. They asked for a spelling. .co.uk. And that's her official personal page. I believe you also have a university. I think you use that very often.
Oh no, they're all joined together now.
Okay, so never mind. Great. So we are wrapping up because, Michael, I would like to thank Michael because he's been awake despite not feeling great, handling the stream. So thank you also Thor, Pookie, and Selfish Pie for joining us tonight. And of course, thank you, Dr. Sarah, for taking your time to play with us and making us like the universe, both the elite one and the real one, even more. Again, Sarah will be accompanying us during the entire journey unless she blows up somewhere, which may very well happen. But in that case, she will jump on someone and keep traveling until Beagle Point and back. So keep tuning in, Distant Radio 3305. We bring both music and science to keep you sane. This has been Nightfall Zero. I will see you out there in the black. Bye-bye.
Bye.
Bye-bye.
Cool. We're out.
That went well.
That was a good show.
Thank you for bringing me in here. I wasn't actually expecting that to happen.
Yeah, not many listeners. I was expecting a bit more. Yeah.
Well,